Hello. Now, today I'm going to talk about acids and bases. So I'm going to do some different lectures, and they probably won't be as long as a typical lecture, like if you're sitting in the classroom. I'm going to break it down a little bit more and just save them in smaller files, so you may not have to watch them all at once. So the first topic I'm going to continue on covering in Chapter 4 is acids and bases. So we talked about acids and bases a little bit when I did the introduction. And we talked about what's known as the Arrhenius definition. So Arrhenius definition of acid is something that produces hydrogen ions when dissolved in water. And the Arrhenius definition of a base is a substance that produces hydroxide ions when dissolved in water. So you've probably always heard like acids and bases and what they're used for. And now we're going to look at the chemical definition of acids and bases. So we have another definition, which is known as the Bronsted-Lowry definition. Bronsted-Lowry definition of an acid is a substance that donates a proton, and the Bronsted-Lowry definition of a base is a substance that accepts a proton. And so the reason it's called a proton is because if you think about a hydrogen atom has an atomic number of 1. So that means it has 1 proton and 1 electron. Well, if it was deficient that 1 electron, okay, it's going to have a positive charge, and all that will be there will be the proton. And so a proton is a way to say it's a hydrogen with a positive charge. And so an acid is something that donates a hydrogen that has a positive charge. It does not have that electron. And the base is something that accepts a hydrogen that does not have that electron. Now in solution, we write this out, a lot of times we'll just write out H+. It doesn't actually exist as H+, it actually bonds to a water molecule and forms hydronium ion, H3O+, but still a lot of times we'll just still write H+, or you could see it written as H3O+ still. And so, look here, we have a couple different examples. So if we look at this reaction, so if we look at HCl plus H2O, so we know this is hydrochloric acid, went over that when we named compounds. So this HCl, what happens to it becomes Cl minus. So it lost the hydrogen. So since it lost the hydrogen, it means it donated the hydrogen. So this would be our acid. Look at H2O. It becomes H3O+. So it gained the hydrogen. It accepted the proton. So that's why this is classified as a base. So water is a molecule that can act as either an acid or a base. So here we see water acting as the base. Like this reaction, NH3 reacting with water. NH3, what happens to it? It becomes NH4. It gained the proton. Okay, so it accepted a proton, so it's your base. What happened to our water? H2O to OH minus, it lost H+. So since it lost H+, then that means it donated the proton, so that's your acid. So here, water's the base, here's water's my acid. So here are some more characteristics of acids and bases. And when you get to Chem 2, okay, now I mentioned something called a pH here. I don't know if you know what pH is, but pH of 7 is neutral. And if you have pH less than 7 is acid, pH greater than 7 is a base. And that actually measures the concentration of that hydronium ion in solution. And so we know if it has a great amount of hydronium ion, it's going to be an acid, because that's what the definition of acid is. But you're going to learn a lot more about acids and bases in Chem 2. Right now it's just a brief overview about acids and bases. So acids are proton donors, have a sour taste, they may sting substances they come in contact with, and they'll turn litmus paper red. So litmus paper is just a piece of paper that's red, and or it could be red or blue. If it's red, you stick it in acid, it stays red. You stick it in base, it turns blue. Likewise, you have blue litmus paper. Stick it in base, it stays blue. Stick it in acid, it turns red. So it's a way to identify acids and bases. Bases taste bitter. They feel soapy or slippery. You get some on your hand. Example of that would be, I don't know if you ever got drain cleaner on your hand. If you ever get drain cleaner on your hand, which is a base, sodium hydroxide, it feels real slimy in water. So that's what it means by feels soapy or slippery. Some examples of common examples of acids would be like lemon juice is acidic, vinegar is acidic, and you can see the pH scale here as well. We can also identify acids as either a strong acid or a weak acid. And when we talk about strong acid or weak acid, it's not really talking about, how bad it is if you get it on you. If you think about it, you may think, well, I'd rather get weak acid on me than a strong acid on me. But that's not the case. There's some weak acids that would really do harm to you if you got them on you as well. And so what it talks about, though, is how it dissociates in water. Okay, strong acids are completely ionized in aqueous solution, so it dissociates 100%. So this is the same as the definition of strong electrolyte and weak electrolyte, which we talked about on Thursday. And so strong acids completely ionized, completely dissociated. Weak acid only partially dissociated, so you have molecules and you have ions both present. So strong acids are listed there: HCl, HBr, HI, HNO3, H2SO4, and HClO4. So there's 6 of them. You need to know those 6. And so just make sure you flashcards out and make sure you know those 6 strong acids, because on the exam you'll be asked a multiple choice question. You'll say, which one of these is a strong acid, or which one of these is not a strong acid, and you have to be able to pick out which one. You need to do that. You need to know which ones are strong acids. So examples of weak acids are HF, hydrofluoric acid, and acetic acid. Acetic acid, the CH3CO2H, is just vinegar. HF, hydrofluoric acid. Now, hydrofluoric acid is an example of a weak acid, but if hydrofluoric acid actually has to be stored in plastic containers, because if you put it in a glass container or porcelain or anything, it'll actually eat through it. So even though it's classified as a weak acid, it's still very dangerous because it can eat through glass. And remind me when I get back, maybe we can look at a scene from Breaking Bad where they use hydrofluoric acid for something. Strong base separates to a large extent to metal ions and hydroxide ions. A weak base produces only a few hydroxide ion solutions. So again, same definition as strong electrolyte, weak electrolyte. Strong bases include the hydroxides of group 1 and 2, so that's easy to remember. Anything that's hydroxide, group 1 and 2 is going to be a strong base. Ammonia is an example of a weak base. So if you look at this example, ammonia with water, it's a reversible reaction, so I have both ions and molecules in solution. Now acids and bases are both very reactive compounds, especially in the presence of one another. Typically when they react with one another, water is one of the products, and we saw this when I talked about double displacement reactions on Thursday. I'll use this as one of the examples. And so water is one of the other products is called a salt. Now, a common misunderstanding when you say produces salt, a lot of people think that, table salt, sodium chloride. Well, sodium chloride is just one example of a salt in chemistry. And so salts are basically referring to any type of ionic compound that has a metal ion and a non-metal or polyatomic ion. So the reaction between an acid and base that produces water and the salt is called a neutralization reaction, because it neutralizes or reduces the effects of both acids and base. So here's the example of your double displacement reaction. And we'll go ahead and work an example of how to write the products of that later on before I'm finished with this lecture. You can also neutralize an acid with a carbonate or sodium bicarbonate. The reaction produces bubbles of carbon dioxide. So if you do the double displacement here, you'll get as one of your products H2O, but then you also, or you get NaCl, but then you also get H2CO3. The H2CO3 breaks on down to H2O, or carbon dioxide. So if you think about antacids, okay, antacids are a carbonate or a bicarbonate, and like you take them to neutralize the acid in your stomach, like if you have heartburn. So if you take that, you're doing a neutralization reaction in your stomach, and it produces carbon dioxide. So a lot of times when you take an antacid, it'll produce carbon dioxide. So what happens? You have to burp to let the carbon dioxide out. And another common example of that is if you ever reacted vinegar and baking soda. So vinegar is an acid, baking soda is a base, sodium bicarbonate. Anybody ever mixed baking soda and vinegar together? What happens? You form a lot of bubbles, and that's from the carbon dioxide that's produced. Now you may have heard the term acids eat metal, and while that's true, it's actually only certain metals. And so acids react with certain metals to produce hydrogen gas and the salt of that metal. And again, when I get back, I may try to do a demonstration on this to show you this reaction and produce the hydrogen gas. So active metals include potassium, sodium, calcium, magnesium, aluminum, zinc, iron, and sulfur. And so you kind of see the reaction going on here. And going back to what we talked about on Thursday, this is a single replacement reaction where our aluminum is replacing our hydrogen, creating the hydrogen gas. So let's practice a little bit on acids and bases now. So it says write molecular ionic and net ionic equations for each of the following acid-base reactions. I'll find some chalk. The first one I have is hydrobromic acid. So hydrobromic acid is HBr. Barium hydroxide. Now you have to remember barium hydroxide. Barium is a 2+. Hydroxide is an OH minus. So if it's a 2+ and I have OH minus, I need 2 hydroxides to balance out my barium. So I'm going to write this out. H+, Br minus, Ba2+, OH minus. So if those react together, okay, I take my positive one first, pair with a negative the second, so that's where I get my H2O. Then I'm going to take my positive my second, pair with my negative of my first, so it's against a 2+, so I need 2 of these, so I'd have BaBr2. Now this says that'd be the molecular. The ionic equation for that, you'd write out all your ions. So H plus Br minus plus Ba2 plus hydroxide ion yields H2O. It's not split down to ions, and then you have your other 2 ions. Plus Ba2 plus Br minus. And so that'd be my ionic equation. So if I cancel out like terms on both sides, the barium and bromines are both gone. So my net ionic equation would just be my H plus my OH minus, yielding my H2O. On this next one, I'm going to skip the ionic one. I'm just going to do the molecular and the net ionic. So sulfuric acid, you have to remember how to name acids and write names for that. So H2SO4. Potassium hydroxide. OH is a minus, potassium is a plus 1, so it's just KOH. So I have H plus, SO4 2 minus, K plus, hydroxide, OH minus. So again, I take positive in my first, earth and negative over here, so I get my water. Positive in my second, earth and negative the first. Here's a K plus, here's a SO4 2 minus. So the formula would be K2SO4 to balance it out. That's my salt. Group 1, so it's going to be soluble. And so if I did my net ionic equation then, I'm going to look and see, you remember when I did net ionic equation, we showed the ions forming a solid. I'm here, I'm going to show the ions forming the liquid. So again, this would be H plus your hydroxide, yielding your H2O. And when you do the net ionic equation or ionic equations, you always include the charges on your ions. So I'm going to stop this video here. So about 16 minutes. So not too bad. We'll do another lesson. We'll look at oxidation reactions and assigning oxidation numbers on the next one. Bye.